Okay, sorry about that. So charging by conduction is when we have these conductors, they physically touch each other, they come into contact with each other, and when coming in contact with each other, these electrons will flow from one object to the other. We're dealing with conductors, so they're able to freely flow. And this is the simulation that I wanted. So when we're dealing with this, what we see first is charging by induction. So I have this neutral electroscope, which is made out of metal, and then I have this negatively charged rod. So I'm going to bring this negatively charged rod over here, and it's going to attract my positive charges. They're going to want to be by the negatively charged object. So bring up my positive charges, or how we actually want to think about it, it'll move away. All of my electrons will move down to these little leafs down at the bottom, which will leave the protons at the top, leaving the top positively charged and the bottom negatively charged. So that's charging by induction. But when I actually physically bring the electrons over there, I have made this negatively charged. I had a lot of electrons on that negatively charged rod, and they don't like being by each other. We'll look at that in a second. They don't like being by each other. So they will be able to spread out more in this electroscope, and they will move to there because they want to be able to spread out. I can do that again. I can keep on bringing charge over there, and it'll try to spread out in a nice optimal way. So charging by conduction, I am just physically bringing the electrons from one conductor to the other, and they are able to move. Um, so then why I had the balloon one is we're really looking at two different situations here. When we charge an an insulator, that's kind of what we see with the balloon. We said this balloon, it's made out of rubber. Well, we didn't say that. Or it's made out of rubber or latex or anything. It's an insulator. It's not made out of metal. So when I charge this up by friction, the electrons will stay where I put them on the insulator. We talked before with the insulator, it has these kind of nice defined structure with the valence electrons kind of staying in place by the protons. That's what we see here. We put the electrons on this insulator, they stay put. But in this case, we brought the electrons on here and they kind of spread out. They are able to move all over the place in a conductor. So let's really quickly just talk about how are they going to spread out and then why will they spread out. So just kind of seeing that again, in a conductor on the right, the way that they spread out is very kind of in an equal way. They're very evenly distributed. If these wanted to be as far away from each other as possible, this is how they can configure themselves to make that happen. So they're going to spread out so that they are as far away from each other as possible. And with the insulator right there where we put them, they don't really have a choice, but the conductor spreading out as much as possible. And the reason that's happening is because of this electric force. So one of the forces we're going to look at is the electric force. And with electric force, we have this idea that like charges will repel each other and opposite charges will attract each other. And what we see in the conductor is we've put electrons on there, these like charges, the electrons are the same charge, the same sign, they are going to then repel each other and spread out in an optimal way, in a way that they are as far away from each other as possible, because these like charges will all be repelling each other. So when we're looking at the electric force, we can say that the electric force is dictated by Coulomb's law, which is this equation that's above me, I think, that says, hey, the electric force is equal to this constant, 1 over 4 pi epsilon naught, times q1, q2 over r squared, where q is the charge of one of the objects, q2 is the charge of the other object, and then r is the distance between them. And I don't think they're going to have any really using Coulomb's law questions because it's just kind of a plug and chug thing. But one thing that we do want to know about is when we're plugging into this equation, why does it not matter which one's q1 and which one's q2? And that's because Newton's third law is going to apply. This is a force, and a force is just an interaction between two objects. We have two charged objects that are interacting with each other. Down here in this little diagram, we have object P is positively charged and object Q is negatively charged, and they're going to have this interaction because they're charged. They're going to have this electric force between them. And we know because of Newton's third law, we have equal and opposite charges on our different objects. Object P is feeling a force of object Q on object P, and object Q is feeling a force of P on Q. So we have this equal and opposite. They have the same magnitude and they're pointing in opposite directions. In this case, they're both pointing towards each other because they are opposite charges. Over here, down below, we see P and Q are both positively charged, but Newton's third law is still going to apply. The force on P by Q is going to equal the force on Q by P, but they will be in opposite directions. So yeah, Newton's third law is still going to apply in this Coulomb interaction. And if we have multiple charges, which again, I don't think they're going to quiz us on, I don't think they'll test us on, but all we have to do is just draw a force diagram and do forces like we always do. So we'll say, hey, which direction are these forces pointing? Determine the value of them, and then add them up like we do with vectors. So we'd have to add them like components. But here we kind of see, okay, we have Q3. We're looking at this point, the charges that are acting, or the force that's acting on charge 1. In this case, we see, oh, Q3 is positive, Q1 is positive. So we have this opposite, we have this repelling force that is acting in a straight line between these two objects. So the force on 1 by 3 is pointing away from these two charges. We see Q4 and Q2 are negatively charged, so we're going to have this attraction because Q1 is positive, so they will attract each other. And again, we'll have this force acting directly from one object to the other one. And yeah, and if we want to figure out the net force, we could just add up these forces in their directions and the components like we usually did. So then just kind of for the last thing, there are 4 fundamental forces that make up the universe. So every single force, every single interaction is dictated by these 4 fundamental forces. And these forces are the strong force, which is a force that holds quarks that make up our protons and neutrons together. We have the electromagnetic force, which is an attractive or repulsive force between two objects with charge. The weak force, which is a weak force responsible for particle decay in the nucleus. And then the gravitational force, which is an attractive force between two objects with mass. And what we'll see, and what we've noticed, because we've done this already, but the electromagnetic force and the gravitational force have very, very great symmetry. They're very, very similar. They're both based on these fundamental properties of our objects, either charge or mass. And another similarity, they both weaken with r squared. When r squared increases, these both get weakened. They both happen at a field, and they're both acting at a distance, and it's based on 1 over that distance squared. Even when we look at these equations, we see these are so similar. They're based on some sort of constant, so 1 over 4 pi epsilon naught, or g, and then this fundamental property of our material multiplied by each other, so Q1 by Q2, the charges, or the masses, which is again another fundamental property, M1, M2, divided by r squared, that distance between them. And then one little final thing, the gravitational force, even though it kind of holds the planets together and everything like that, it's actually a very weak force. If we look at this constant in front of it, it's 6.67 times 10 to the negative 11th, which is a really, really low number. So yeah, we have the Earth kind of holding the moon in place and the sun holding the Earth in place. And that's really just happening because the masses are so big. So gravitational forces, we're more used to them happening at a distance, but it's relatively pretty weak. It just kind of really has a big effect on very massive objects. And then again, like us being held into place and things falling, that's happening because of the gravitational force. But when we're looking at it as like little point particles, it's going to be a relatively weak force. And then the electric force is going to be a little bit stronger. But when we think about charges, the charge is going to be really weak. They're going to usually be on the scale of like nanocoulombs, so like times 10 to the negative 9th coulombs. And the constant is going to be 9 times 10 to the 9th. So it's a pretty big constant. If we kind of plugged in a big amount of charge, we would have a very, very strong force. And this electric force, we're used to it happening on a very small scale. It's used to these particles being really, really close together, as opposed to the gravitational force where they're happening far away from each other. That's kind of what I got. I'll have a few quick practice questions, but nothing too long, hopefully. And yeah, so hopefully that was okay.